Chapter 5.2, use perpendicular bisectors. Okay, so a segment, ray, line, or plane that is perpendicular to a segment at its midpoint is called a perpendicular bisector. Let's take a look. So right here we have line segment AB, and we see that P is the midpoint. How do we know that? Because the segments surrounding P are congruent. Okay, and since line CP goes through the midpoint and it's also perpendicular, that makes CP a perpendicular bisector of line segment AB. Okay, remember this symbol here means perpendicular. A point is equidistant from two figures if the point is the same distance from each figure. Points on the perpendicular bisector of a segment are equidistant from the segment's endpoints. So basically what that's saying is, if you take any point, this is the perpendicular bisector, if you take any point on that line, then it will be the same distance from any point on the perpendicular bisector is the same distance to both endpoints. So this and this are going to be the same length. So we'll get into that a little bit later. All right, so here we are, perpendicular bisector theorem. In a plane, if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So let's take a look. So right here, you can see that line CP is the perpendicular bisector. It's perpendicular, and you can see the segments surrounding P are congruent, so it bisects or cuts the line segment in half. So if you recall, bisect means to cut in half, and as a result, you can take any point on this line and it's going to be the same distance to A and the same distance to B, basically the same distance to the endpoints. So AC is congruent to BC. All right, and there's a simple reason that that's true. Let's say we didn't know those blue segments were congruent. We can still prove these triangles congruent. Okay, if there's a right angle here, then there's a right angle here as well. All right, and this side right here is shared by both triangles, so I can mark that congruent. So these two triangles are congruent by side, angle, side. Side, angle, side. Okay, they are congruent by SAS. All right, and if these triangles are congruent, then the corresponding parts are congruent. So this side here corresponds to this side here. Since both triangles are congruent, those sides are congruent. Okay, the converse of the perpendicular bisector theorem. In a plane, if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. Let's take a look. So right here, you can see point D is the same distance to both endpoints. Okay, if you go to B and if you go to A, that is going to be the same distance. So DA matches DB, or they're congruent. And since they both intersect at point D and they're both the same distance to the endpoints, that means that point is going to be on the perpendicular bisector. So point D is actually on line CP. So if you didn't know this theorem, but you just extended this line right here, all right, if you didn't know the theorem, but you just extended the line, and let's say for the sake of argument, you stopped at point D. All right, you just drew that line right there. This side is shared by both triangles, so I can mark that congruent to itself. And then we have side, side, side. side, side, side. And if these two triangles are congruent, this angle would have to match that angle. So they would both have to be 90 degrees. All right, so even if we didn't know it was perpendicular, the triangles are congruent by side, side, side. So they are congruent by SSS. Example 1, BD is the perpendicular bisector of AC. Find AD. Let's take a look. All right, it said BD is the perpendicular bisector. So that means right here, it's perpendicular. It's going to make a right angle on both sides. And this segment is congruent to that segment. And of course, this one right here is shared by both triangles. So these triangles are congruent by side, angle, side. Side, angle, side. The congruent angle is in between the two congruent sides. So they are congruent by side, angle, side. All right, and since these two triangles are congruent, I know that this side here is congruent to that side there. Okay, so they wanted us to find AD, but first we have to find X. And if these two sides are congruent, we can just set them equal to each other. So AD equals CD. Okay, AD equals CD, equal length. And AD is 5x. And CD is 3x plus 14. Okay, subtracting 3x from both. The 3x's cancel. 5 minus 3 is 2. And bring down your 14. Dividing both by 2, x equals 7. All right. So once you have that 7, you just want to plug in. All right, they said AD, so that's this one right here. And we're just going to plug in the 7 in place of x. So you put 7 right there. Of course, 5 times 7 is just 35. So that's this side here. That's AD. All right. If you want to double check, if you put 7 in here, you get 3 times 7, that's 21, plus 14 is 35. Example 2, in the diagram, WX is the perpendicular bisector of YZ. Part A, what segment lengths in the diagram are equal? Okay, let's take a look. All right, it says WX is the perpendicular bisector of YZ. So they already showed it was perpendicular. And if it bisects this right here, that means this has to match that. Okay, so YX equals ZX. Or we can say YX is congruent to ZX. Basically the same thing. And obviously, we already know that YV equals ZV because that's given in the diagram. So I won't even write that one. But if it's perpendicular here, one right angle, there's going to be 4 right angles here. So this is a right angle. And this is a right angle. Okay, and this side right here is shared by both of these triangles. So I can mark that congruent, and we have side, angle, side. Side, angle, side. All right, if these two triangles on the bottom are congruent, then this one here is going to match that one there. So WY is congruent to WZ. Part B, is V on WX? Let's see. Okay, this point here, is that on WX? Absolutely. We said in the previous theorem, if a point is the same distance to both endpoints, so we can see right here is 25 and right here is 25. This point is the same distance from Y to Z, then that means that point is going to be on the perpendicular bisector. It's given in the problem that WX is the perpendicular bisector, so that means V is going to be on the perpendicular bisector. All right, V is on the perpendicular bisector since it is equidistant to the endpoints. Equidistance means it's the same distance. You can see right here it's 25 on both. All right, and we said that before. If the point is equidistant from the endpoints, then it is on the perpendicular bisector. All right, let's check out guided practice. JK is the perpendicular bisector of NL. Let's try number 1. Which segment lengths are equal? So please tell me which segment lengths are equal. All right, if JK is the perpendicular bisector, it's bisecting this right here. So this one, which is NJ, is congruent to this one, which is JL. All right, so NJ is equal to JL, or you could say they are congruent. You can make it equal without the bars or congruent with the bars, same thing. And this is obvious right here, so I'm not even going to write it. 8 matches 8. But you can see right here, this side is shared by both triangles, and we have side, angle, side, side, angle, side, all right? This right angle is also here as well. And as a result, this side is going to match this side. So NK matches LK. NK matches LK by side angle side. All right, and these two here, it's just because of the definition of bisect. All right, we said this was a perpendicular bisector. Bisect means to cut in half. So that's how we know those are congruent. All right, one of them is because it's bisected, and the other one is because of side angle side. All right, number 2, find NK. Let's take a look. All right, please see if you can find NK. I'll give you a hint. Since these two are congruent, you can just set them equal to each other. Solve for X and plug it in. So we said these two are congruent. That means they have equal lengths. All right, NK, we can see that's 6x minus 5. LK is right here. We can see that's 4x plus 1. All right. I like to subtract a smaller x, but it doesn't matter. So minus 4x on both. 6x minus 4x is 2x. Bring down the equals, and the 4x is canceled. Since I have variables here, I want constants over here, so I'm going to get rid of this negative 5 by doing the opposite. Plus 5 on both, and that cancels. 1 plus 5 is 6, and of course, dividing both sides by 2, x is 3. Now, they said they wanted NK. So we have to take that and plug it in. All right, so you put the 3 in there. And that's going to be 6 times 3 minus 5. 18 minus 5 is 13. Final answer. If you want to double check, take the 3, put it right here. 4 times 3 is 12, plus 1 is 13. So it checks out. Finally, explain why M is on JK. Let's take a look. All right, here's point M. And we can see it is the same distance to the endpoints of the segment that's being bisected. Okay, so M is equidistant to the endpoints. When that happens, that means it's on the perpendicular bisector. All right, so the definition of concurrency, that is when three or more lines, rays, or segments intersect in the same point. They are called concurrent. And the point of intersection is called the point of concurrency. Okay, so basically three or more lines, rays, or segments intersect at the same point. That means they are concurrent. Concurrency of perpendicular bisectors of a triangle states that the perpendicular bisectors of a triangle intersect at a point that is equidistant from the vertices of the triangle. Let's take a look. All right, so let's see. The perpendicular bisectors are the ones in blue. All right, we have this one here, this one here, and this one here. All right, remember the perpendicular bisectors, they make a right angle with the side, and they also bisect the side. They cut it into two equal halves. So all three perpendicular bisectors meet at the same point, and the theorem states that that point is the same distance to all the vertices. So the distance from that point to A, the distance from that point to C, and the distance from that point to B are all the same length. So this segment and this segment here are all the same length. Example 3, it says 3 snack carts sell frozen yogurt from points A, B, and C outside a city. Each of the 3 carts is the same distance from the frozen yogurt distributor. Find the location for the distributor that is equidistant from the 3 carts. So here's just a sketch real quick. These are the carts. We have A, B, and C. Okay, and what they did, they constructed a triangle out of A, B, and C. All right, so they did that. And once they constructed the triangle, they drew in the perpendicular bisectors. So you see here, this blue line, it's perpendicular and it bisects. Same with this blue line segment and same with this blue line segment. Okay, they all meet at point D. And we said a minute ago, the perpendicular bisectors meet at a point that is the same distance from all the vertices. So D is the same distance to C, the same distance to A, and the same distance to B. All right, so in that case, the carts A, B, and C are all the same distance from the center. So the distributor is the same distance or equidistant from the 3 carts. So point D would be the location of the distributor. All right, guided practice 4. Hot pretzels are sold from points A and B and also from a cart at point E. Where could the distributor be located if it's equidistant from those 3 points? Let's take a look. All right, so see if you could just draw a rough sketch of a triangle at points A, B, and E. Draw in the perpendicular bisectors, and then you will see they're the same distance from all the vertices. All right, I'll start with the triangle. So I'm just connecting points A, B, and E. All right, so I'm going to draw in the triangle. All right, and then I'm going to draw in perpendicular bisectors. So I'm going to start at the midpoint of each one. Start at the midpoint of each one, and I'm going to try to connect them at the same point. So if I go like this, and then this, and then that. All right, I'm just doing a rough sketch here. It's not going to be perfect, but if I draw it like so, they all meet at this point right here. Okay, so this is supposed to be a right angle with each side. And of course, it's supposed to bisect each side. It's supposed to cut each side in half. Okay, so that point right there in the center, that's your point of concurrency. All right, so that point in red is the point of concurrency. And that is the same distance to point A, to point E, and to point B. Same distance. All right, the point of concurrency of the three perpendicular bisectors of a triangle is called the circumcenter. So that point where the perpendicular bisectors meet, that's called the circumcenter. All right, and the circumcenter P is equidistant from the three vertices, which we said already. So P is the center of a circle that passes through all three vertices. Let's take a look. Okay, so these lines in red are the perpendicular bisectors. And see how for this triangle they drew a circle so it meets, the circle meets all three vertices of the triangle. Okay, and point P is the circumcenter, but it is also the center of the circle. So this one is an acute triangle, and P is inside the triangle. So in all of these examples, P is the circumcenter. Okay, that's where all the perpendicular bisectors meet. So for the acute triangle, the center of the circle, P, that's inside the triangle. Then for the right triangle, again, you draw the circle so it hits all three vertices of the triangle. You draw in the perpendicular bisectors, and they meet on the triangle for a right triangle. Okay, and finally for an obtuse triangle, again, you draw the circle so it hits all three vertices of the triangle, and the circumcenter, where the perpendicular bisectors meet, is outside the triangle for an obtuse triangle. See this angle right here? That's obtuse, that's greater than 90. So to sum it up, the acute triangle, the circumcenter is inside. Right triangle, the circumcenter is on the triangle. Obtuse triangle, the circumcenter is outside. All right, and last definition, when you draw the circle around the outside of the triangle, the circle is said to be circumscribed about the triangle. So when the circle is on the outside, circle is outside the triangle, it's said to be circumscribed.